Right, so our fourth speaker for this session is Igor Soe from the Technical University of Munich, and he's going to present his work on 4D-OR, semantic scene graphs for OR domain modeling. So welcome to the speaker.
Okay, so thank you for your kind introduction, and hi everyone, welcome. Today it's a great pleasure of mine to present to you 4D-OR, semantic scene graphs for OR domain modeling. Just a second. Perfect. So I want to start with one question. When we watch this surgery video together, maybe this better. Can we understand what's happening here? And we all have different backgrounds. For some of us, it might be easier than for others, but I think most of us can, on a higher level, understand what is going on in this surgical operation. And I would even argue that expert surgeons among us can not only understand what is going on, but why is it happening exactly, and like really in a fine level analyze and summarize the surgery. I want to follow up this with a second question, which is, as of today, do we have any digital system that can understand what we have just understood together? And I would argue the answer today is still no. Indeed, it's true that we have a lot of works that are focusing on workflow detection. Some of them, early works focused on summarizing a surgery as a feature vector by using the electronic signals. Recent works especially focused on using laparoscopy video combined with deep learning to analyze faces, some actions, etc., as we also heard today. But no method so far has focused on fully understanding the complex interactions and activities that happen in an operating room. What do I mean by when I say holistic OR understanding? I'm talking about capturing the entire complexity in there. And why is this necessary? There are, of course, many examples of this, but some are decision support systems that support the clinical staff during the entire surgery, context-aware and intelligent systems that can adapt their state, their function, and also their interface to the surgery in progress, and also to each other. The question here is, do we know how to get there? So how do we go from where we are today to developing intelligent models that capture this complexity? And I hope to give one possible solution to this today. For that purpose, I want to shortly introduce scene graphs from the computer graphics community, which have been used since early 1990s to model complex environments and the interactions the entities have in them. As an example, Pixar introduced universal scene description based on scene graphs, which is one of the industry standards here. What happens usually is they describe a scene using the nodes to represent the entities, and then they also represent the interactions they have. And then we have the forward problem here, where we go from scene graphs to a scene. In the recent years, the computer vision and machine learning approaches have allowed the community to tackle the inverse problem, where we have a scene, mostly the focus has been on natural images, and then we go from this scene into a scene graph by using different techniques. This scene graph then captures the essence that the scene has. And this has still not really been applied for very complex scenes and also not for modeling operating rooms. So specifically in our work, our main contributions are twofold. First, we create and release the first 4D-OR dataset with semantic scene graph annotations. Second, we propose the first approach towards modeling the complex surgical procedures using semantic scene graphs. When we have started this work, there were a couple of datasets available. One of them was MWOR, which has around 700 frames from real operating rooms, and it also has labels for human poses. But it was never created to capture the complex interactions that happen in an operating room, so it doesn't have the interesting semantic interaction labels that we want. The public version of this dataset is also not a temporal dataset. The second dataset from Shargi et al. Is much bigger. It includes about 400 full-length multi-perspective videos from robotic surgeries. But as previously was the case, this was also not created to capture the complex interactions that happen in a surgical room. So the annotations are mainly just for the 10 most common phases on a frame level, and the dataset as well is not publicly available. Here we come to 4D-OR, which consists of 10 simulated total knee replacement surgeries, and our data type is 3D plus time, so we have point cloud sequences in 1 frame per second. We have annotations for 3D human and object poses, and most importantly for this work, we have semantic scene graph labels that describe the complexity in the scene. We also have clinical roles for every human that appear in our scene. As you can see, we have depth information, and we can visualize the entire thing in 3D as well with time. I want to go over 2 examples here to give you an idea of what these scene graphs are able to capture. Here we can see an example with 3 humans. The human 0 in this case is the patient, and he is lying on the operating table. Human 1 is drilling into the knee of human 0, and that's also captured. This is the head surgeon. And finally, we see human 2 assisting human 1, and he's the assistant surgeon in this case. Both are holding an instrument, which is also captured. In the second example, we have a cleaning scene, sterilization before the actual surgery starts. And I want to focus on this part especially, where you see the circulating nurse touching the table. And this is not traditionally would be considered the essential part of the surgery, but the point here is the scene graph really tries to capture everything that happens in the operating room, not necessarily only the most interesting part. Once we have a data set like this, we can go on to create a method that is able to automatically generate such a scene graph. We start by using the multi-view 2D images as well as the 3D point clouds and apply state-of-the-art human pose detection and object detection algorithms on top of them. Once we have captured the humans and objects, we now have our entities in the scene, and we can move on to generate the scene graph. Here we start with 3D SSG, a popular method from the 3D computer vision community, but we first changed the encoder from PointNet to PointNet++, which is able to capture the hierarchical and small details in a scene much better. Secondly, we employ some OR-specific augmentations to improve the generalizability. And finally, and most importantly for us, we extend 3D SSG to be a multimodal approach that doesn't only rely on point clouds, but instead uses images as well. Why is this very important for us? As you can imagine, in an operating room, most complex interactions are defined by small, transparent metallic tools, which are very hard to capture in the point clouds. By using images, we make sure to capture these semantics from the scene as well, improving our results on these cases a lot. As of this moment, we have a scene graph with human nodes such as human 0, human 1, etc., but we don't know the roles of them. So what do? We use actually a downstream task to compute the roles, and the role computation is done only by relying on the scene graph, demonstrating the power and summarization capability of them. Predicting the role can be quite difficult from a single scene, depending on the ambiguity. So instead, for every human node, we track them and look them over time and see in which kind of interactions they had over the entire surgery. Once you know this, you can use either heuristics or a learning-based method to predict what the likelihood of this person is, that it is a head surgeon, patient, etc. I have already gone over some qualitative examples before. Those were actually already predictions, what I showed. The right 2 examples are also new. You can take a look at them shortly. We see they are really different and capture different semantics, such as operating the table, holding instruments, etc. Quantitatively, we get a macro average of 75. On 2 relations, as an example, such as close to and lying on, we are really good. These can be considered more easy relations, of course. On some of them, we perform worse. And here I want to specifically point out cutting and touching, which can be quite easy to confuse with each other, because if you think about it, the main difference is if the surgeon is holding a very small scalpel in his hand or not, and this can be hard to understand from images. So actually, if you look at the confusion matrix, you would see that they are getting mixed up with each other. In role prediction,
1 minute.
both methods perform well, but Graph-Former performs a little bit better. Here, it really depends on the application. Heuristic-based has the advantage of being transparent and having a fast run time, whereas Graph-Former is really easy to adapt to new roles, surgeries, without the need to change any rules. We can bring all of the information we capture together by detecting the objects, the humans, generating a scene graph, and finally, from the scene graph, we can predict the roles, and also a phase label, as you can see in the bottom. So in conclusion, we released the first OR dataset. Our dataset code and evaluation website are all public. You can already access it. There's a benchmark. And the future, we imagine bringing more signals, capturing external and internal events, and integrating all of them so that our semantic scene graphs capture all the complexities there that are available in an operating room. And finally, extending this to real-world, multi-centering, multi-surgery data set would make them much more robust and much more generalizable. Thank you very much, and feel free to come to my poster afterwards.
Thank you so much. Really exciting work, and really good to see such a great data set being made publicly available, such a rich data set. My question is regarding the relations or the joints that you created. So for some of the joints, of course, the performance seems really good, but for others, it's not as good as we expect. So do you want to comment on that?
Maybe I can actually go back or not. Yeah, so I would say in that regard, some of them, such as sawing or drilling, are characterized by very distinct instruments, such as a kind of green saw in our case, or a red drill, which make them easier to detect. Some of them, such as suturing, I mean, you can imagine we are talking about very small metallic needles that have to be understood correctly. And right now, the baseline method does not use the temporal component. It evaluates every frame on its own. So you really have to just see the scene and make sure, is the surgeon touching the patient or suturing the patient? And that can be quite difficult. That would be my reasoning for that.
Okay, yeah. We have one question over there.
Yeah, thanks a lot for the interesting talk. It was really cool work. I just have two questions. One technical, which is how do you deal with redundant actions? So if you have an action that's not described in your training data sets, how do you deal with that? And the more general one is more about maybe it's not clear for me, what's the motivation behind this work? Can you elaborate more on that?
Mm-hmm. So I'll try to answer them one after another. If you don't have an action that you defined, what would happen right now, it would of course predict something that looks as close to it as possible. If you have never seen something, it's not going to be able to predict that correctly. But some of these actions that we have here, such as close to, touching, lying, are more generalizable. But if you, of course, go to other surgeries, it wouldn't immediately know a new action. On the other hand, you can extend, I mean, we are trying to propose a concept here. You could keep extending the scene graph and which relations you're interested in so that you support them. On the second point, which is the motivation, I would like to say, like, if you can imagine maybe an analogy of autonomous cars, if you're able to understand every car in the scene, every stop sign, the road curvature, and that the car is now waiting for that pedestrian to cross over, and all these complexities, writing a road planning algorithm becomes much more easy. And we imagine this the same way as well. Once you are able to semantically understand the complexities that happen in an operating room, you can achieve tasks that you didn't even plan to achieve before because you realize now they became so easy. This was the case actually for role prediction for us, and also for the face labels. You could just achieve them with some rules that process the scene graphs.
Yeah, can I add more?
Feel free.
Do you see any similarity if you have like two different operations on the same operations? Do you see the same graph in the end? Or?
Yes, so right now I would say that we don't have enough variability in our data set to correctly answer this question. Therefore, I would refer on, I would not really comment on that much, but that's definitely an interesting thing, and we should try to go in that direction.
Yeah, thanks a lot.
Thank you.
Yeah, one final question from at the back. Yeah.
Hi, thanks. Very interesting talk. I was wondering if you noticed any difference in performance when just using the 2D image information versus 2D plus point cloud?
This we could also discuss in detail in the poster session. Right now, the formulation that I did here does not allow to use only 2D images because it's quite complex, a technical challenge. You would have to crop the image a lot, and it increases the burden on computation. I have ablations that do just 3D versus 3D plus 2D. I can imagine 2D alone working quite well for some tasks. Some of them, such as being close to something, could be quite more easy to achieve with 3D, of course. So this is something that one would have to look at. But of course, very interesting because 3D capturing can be more costly and more expensive.
So yeah, now let's thank the speaker once again.
Thank you.